Okay, in this video we want to start measuring. We want to measure with numbers and formulas and so on. What happens to the temperature of things when you add heat to them? Alright, so there's two main ways of talking about this, as long as the substance does not change phases, which is a topic for a later video. As long as the substance stays in the same phase, then we can talk about these two kinds of measurements. The first one is called thermal capacity, and the other one is called specific heat capacity. Now, this kind of belies the subject here, but the specific heat capacity is more important, even though I've titled it as thermal capacity. Anyways, so basically what's going on is we're heating things. Here's a pot being heated over a wood fire, and then here's a blacksmith heating a piece of metal inside his fire. So the kind of thing that you're heating and the size of it matters, depending on whether you're talking about thermal capacity or specific heat capacity. So the question is, how hot do things get when they're heated? Okay, so first, thermal capacity. Bam! Thermal capacity, it measures the temperature rise of the object as it's heated compared to how much heat was added to the object. Alright? So I've got here, you can probably tell this is actually the same picture, but the point is, just to illustrate, if you have a small version of an object and a large version of an object, and let's just say they're identical, which in this case they are, they're just different sizes, made of the same exact material and so on, then the question is which one has more thermal capacity? Which one is going to have a bigger temperature rise if the same amount of heat is added? So the same amount of heat energy is added to this guy, same amount of heat energy added to this guy. So let's just say it's, I don't know, 1,000 joules. Alright, 1,000 joules of heat energy to this guy, 1,000 joules of heat energy to this guy. On this guy, big one, there's a whole lot more atoms there to absorb the energy. This one, way fewer atoms to absorb the energy. So actually what happens is the temperature rise in the bigger object is going to be less because the heat gets more spread out. It's got more space to diffuse, to spread around through the material. So the average kinetic energy increase inside this object is going to be less because there's more atoms to absorb the energy. So in here, fewer atoms to absorb the energy, it's going to have a greater increase. All right? So a greater increase in temperature in the small guy. Boom, we'll just illustrate it with a big arrow versus a small arrow. All right? So a bigger temperature rise in a smaller object and a smaller temperature rise in a big object. All right? So that means basically the big object has more thermal capacity. It can take more heat with less temperature rise. So more heat energy causes a less temperature rise than this guy would have. So that we call that the thermal capacity. Basically, that's how much energy you can add to the material with compared to its temperature rise. And you call it a higher thermal capacity if you can add a lot more energy for the same rise in temperature. All right? So this guy, just to say it one more time, you can add the amount of heat required to cause this guy's temperature to increase by a specific amount, say 1 degree Celsius, is greater because it's bigger. So you need more heat to cause 1 degree change in the big guy than you need in the small guy. Smaller amount of heat to cause 1 degree temperature change in that guy. Alright? Alright, so now, what if we want to talk about the heat added and the temperature rise of a particular substance without reference to its size? What if we want to have like a number that represents all aluminum everywhere, no matter how big or small it is? That number is called specific heat capacity. All right, and that tells you how much 1 gram of a substance how much heat would be needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay, so it's very specific. How much heat is necessary to raise 1 gram of, for example, aluminum by 1 degree Celsius? And then how much heat is needed for that? How much heat in joules? All right, so that's specific heat capacity. It's all the same for a specific kind of metal or any kind of substance. Every kind of substance has a specific heat capacity. It's just easiest to refer to metals. Size does not matter. If these are all the same metal, they have all the same specific heat capacity, all right, which is abbreviated as C. Okay, so that's the important thing with specific heat capacity. It is unique to a substance. It is a property of a material, and it does not change based on size. All right, regardless of size, it does not change. Specific heat capacity of aluminum, for example, is always the same as long as you have pure aluminum. All right, so let's get down to the formulas here. How do you calculate them? I'm not actually going to do any sample problems in this video because I don't want it to be super long. We'll do that in class. The main thing I want to show you here is the actual formulas, and hopefully seeing these you'll be able to tell the difference between the two even more clearly. All right, so thermal capacity, we said that's the one that depends on the size of the object. The only two things we're concerned with are the heat added and the change in temperature. So you take the amount of heat added in joules and you divide by the change in temperature, either in kelvins or degrees Celsius. Usually we'll use degrees Celsius. And then this is what you get in symbols. Q, capital Q, is what we use to represent heat energy in joules. And then delta T, delta refers to change, T, capital T, is temperature, so change in temperature. Okay, so we don't really have a symbol to represent thermal capacity. I suppose you could use a capital T, capital C, or something like that. But anyway, we're not going to do problems with this often enough to really need an abbreviation. So anyway, that's it. Q divided by delta T. All right. What about specific heat capacity? Well, specific heat capacity is equal to heat added divided by, so heat added again, temperature change again, also there. But we have mass now. So heat added is divided by the mass times the temperature change. Okay, so what's that look like in symbols? It looks like this. We abbreviate specific heat capacity as a little c. All right, right there. So in symbols, this is your formula for specific heat capacity. And this is important. This is a very important formula. You will need to know this for sure. You need to be able to work with it and solve problems with it and so on. Given 3 of these 4 variables, you need to be able to solve for the 4th one. I mean, that's basic algebra. But you need to know this formula. C equals Q divided by M delta T. All right. If you want maybe a clever way to remember this, you can remember, like, I'll draw it out here. Q equals M cat. Q equals M cat. Wait, what? Well, here, let me show you. Q, if we rearrange that formula, it's equal to mass times C, the specific heat capacity, times change in temperature. So you can see how that kind of looks like MCAT. All right, so Q equals MCAT. All right, if you want a clever way to remember that. But then if you're solving for C, you'll have to rearrange the formula using your algebra, and that will take you back to this. Okay, cool. That's all I've got for you. Thanks for watching, and I'll see you next time.